okay, let's just
To start? Okay, wonderful. Yeah, thank you for the introduction, Max and Roy. It's always great to be here and talk to all of you and hopefully find great connections between what Google is doing in the space of IoT and what we've been doing at Carnegie Mellon. A lot of the work that I'll present today is actually part of our larger team. Anil and I are here, and a number of our students who sort of set up the demos. Some of the other faculty members couldn't make it because it's the middle of the semester and sort of some other events happening at the same time. So the first talk, I'll present the first two talks. The first one is really an overarching vision of what we wanted to get to, what have we sort of been able to get to in the last year and a half, and then we'll have specific talks about security, privacy, and safety, which will be my second talk. Then there will be a talk on machine intelligence, machine learning, and by Anil, and then another talk by him on the end user programming. So we'll have the next 2 hours should give you a good flavor of where we are in terms of Giotto. So the overarching goal of Giotto was to sort of build a safe, secure, and easy to use IoT infrastructure. That I guess is what everybody, I'm sure it resonates with all of you, because that's what we all want to do. So our vision at a high level was to sort of enable a successful IoT ecosystem such that sort of life becomes easier and richer to this adoption of IoT. And, you know, there is various things that you'd want to do, right? You want to be able to discover and interact with these connected devices in a way that application, user experience, and then development becomes a lot easier, while making sure across this whole ecosystem, we are taking care of privacy and security issues. And, you know, at a fundamental level, make sure that this IoT ecosystem has some interoperability so that, you know, we're not like, we don't have a bunch of fragmented systems together. We wanted to make sure that it's modular. It has actually scales starting from at the level of smart buildings, as Roy and Max mentioned. Our first goal was a living laboratory at our campus, but then also scale it to the scale of a smart city such as Pittsburgh, promote interoperability, as I mentioned, and then allow the ability to sort of build and share apps that primarily first at least enhance campus life. So everything around the campus, or what is on a campus and how to improve the life of students, faculty, as well as operations on campus, and also primarily provide a test bed for prototyping and evaluating ideas.
Do you want questions now, or?
What question do you have?
We have enough flexibility in time.
Yeah. So yeah.
Yeah, I mean, vision-wise, I'm not quite sure what you mean in terms of modular. Typically implies a bunch of modules. It's very different than in a box concept. In a black box, here's a thing.
Yes. Yes.
You know, they lead to very different architectures and systems and ecosystems and all that stuff.
Yes.
So if you can clarify that.
Yeah. So I think the goal is to sort of enable both, in the sense that it should be for people who don't want to muck around with the actual stack and just want to be users of the stack. There should be a version of the stack that allows you to just deploy it and use it easily, versus for developers who may want to extend the stack in particular ways.
If you can't have both, which way do you lean? Because those are two, I mean, my experience is those are two very different models. So I understand ideally both, yes. Which way does it go?
If it's user-focused, it should be IoT in a box that people can actually use and deploy. Right? But for many reasons, including working with people like Google and other places, it looks like modularity, some level of modularity will be needed. It may not be the most perfectly modular system, but some level of modularity is almost essential so that you can support different technologies. Okay, so now there are a myriad of IoT efforts. Like we had this slide before, and some of you may be seeing this for the first time. I wanted to put out some bullets that actually talk about how sort of perhaps our IoT effort is different, or what we think is the differences with respect to other academic as well as other efforts. So first of all, this is a living laboratory test bed. Whatever we do, we deploy in our own buildings and our own campus. And I'll talk about it. We've actually got large-scale applications deployed across multiple years now. And this is like we're living in these buildings that are run by this sort of Giotto stack. We are looking at hardware, so often we're leveraging commercial off-the-shelf hardware, but also developing new ones where we find that there are gaps that current hardware doesn't do, so which is actually a difference from other IoT efforts as well. Privacy and security is actually pervasive across the entire stack, which we thought is a pretty big differentiator with respect to other efforts as well. We're also integrating machine learning at multiple levels. We're leveraging edge and cloud computing so as to provide a flexible architecture of where you're doing the processing. So not just in the cloud, but perhaps a distributed architecture where some process is happening much closer to the sensors which are generating data. And we are very focused on sort of the end user experience and the end user programming. Again, a lot of the faculty members a lot of our collaborators are actually people who have experience with HCI. So we were very focused on the end user experience. Many of the issues were coming from there. We also have extensive experience on deploying systems at scale. As I said, some of our smart building OSs have been used across 50 buildings already. So we have a history of doing that. So our expedition team comprises of Anand and I, who are leading this expedition. And then we have a number of amazing colleagues who are working on specific aspects. So end user programming, HCI, smart building, security, privacy, machine learning, edge analytics, middleware and scalability, as well as the underlying sensors and actuators in terms of developing new sensing modalities. So we have part of the expedition is 6 core faculty. And then there is another group at Carnegie Mellon also working on other privacy issues, Norman Sade, Lori, and Luyo. And what you can see at the bottom is as part of this program, Google also supported Cornell Tech as well as Illinois as sort of spokes. Think of it as a hub, and then some other spokes where they were looking at security and privacy issues as well. Yeah. Okay. So this is what pick your favorite picture of a stack. This is what it looks like. So our system stack also starts at the bottommost layer of like sensors and actuators, data integration middleware, edge analytics, and then all the way up to end user environments. And I'll talk about exactly what each of these layers do. And some of these layers will actually have entire talks in the later in the day as well as in the afternoon. But overall, our goal was to sort of define a hardware software stack to enable this ecosystem with all the sort of keywords that I was talking about in terms of extensibility and modularity. As Trevor pointed out, it may mean different things depending on who you want to cater to, whether it's developers or actually end users, integrated machine learning, but overall enhanced human-to-human and human-to-environment interaction. I want to point out, initially, we were focused on buildings because it was a living lab, but the goal is to expand out generally to more IoT and smart cities. So let's start with the topmost layer. So the overarching vision of what we were thinking about, what we wanted to enable, was to enable this sort of new, I'm sure all of you are familiar with this assistants, right? You're familiar with Siri, you're familiar with, you're familiar with all of these new assistants that are coming out, right? The most of the part that we found out is most of these assistants are really only parsing information and providing you these important cues based on virtual information. So things from your apps, things from your email, things from your calendar. What is really perhaps missing is information that they can get from your physical world all around you, right? So think physical meets virtual, and then think of a much more omnipotent assistant that can provide you not only contextual cues and data just in time without you even asking for it, but that is actually actionable. So that is what we wanted to get to, so that you allow people the sort of information to be pushed to users without them even knowing, based on interest gathered from both real world interactions, based on physical sensors around them. Often a lot of those are inferred. Right, and you want to do all of this because while taking into account privacy and programmability, because these we think are one of those fundamental issues that often all of the extra functionality comes at the cost of privacy, and we wanted to make sure we tackle these from ground up rather than do a bolt-on solution later to try to deal with them. In terms of end user support, we're looking at things like what are the different ways of being able to sort of allow people to program these. Who are the programmers? Is it going to be everybody who's at Google, or is it going to be people who have never written a single line of code? That means that you need different sort of metaphors in programming, whether it be visual, whether it be more natural language based. And the idea is that you provide not only the underlying mechanisms such as APIs, pub/sub methods, etc., to enable you to write applications, but also layer the right visual programming or other programming metaphors that allow even non-programmers to be able to represent applications. And then in terms of developer tools and APIs, again, the target is, we were trying to target both, but at the very least, you want to make sure that people who want to write applications and use the system, it should be easy to deploy, like such as an IoT in a box. Somebody at Google was pointing out that could it be as easy as just doing apt-get install Giotto to be able to like install whatever your stack or have it in a package version that becomes very easy. Also, it's easier to incorporate and build new virtual sensors and actuators, so it'll be clearer of what this means in a few slides. And ideally, the modularity argument is that you should be able to extend the stack and plug in replacements for different pieces. So if tomorrow you want to replace some parts with the Google technology or some other technology, you should be able to do that without having to make major large-scale changes to the stack. So let me give you an example of what sort of one of the IoT relevant abstraction means in this case. So what we observe first is often the abstraction of being able to get sensors and actuator data is often at the wrong level, right? Often what will happen is when you're writing applications for these devices, you're thinking about, let me get the raw accelerometer data, or let me get the temperature reading, and then you write an application to take all of that data and be able to convert it into some meaningful inference or something that people can actually use. So what we felt was really the semantic information gap of what people actually want or what is useful versus what the data at the level that you get is actually pretty large. Often people may, or users or application, all they may want is the door open or closed or not? Is this talk exciting or not, right? Is this room completely full or not, right? You want these higher level inferences as opposed to the raw fine-grained data, right? And often you can use that fine-grained data to make inferences, but most people don't necessarily want to do that, right? It's at the wrong level of abstraction. So one example that we've been doing to sort of alleviate this is to sort of this idea of programming by demonstration. So the idea is that people or anybody using the Giotto stack should be able to create their own virtual sensor that is a learned combination of various different raw sensors, whether it's using machine learning, whether it's using just a mathematical combination of different sensors. But the idea is that you deploy something and you say, I want to deploy a new virtual sensor. There's various states that this virtual sensor can be: door open, door closed, talk exciting, talk not exciting, right? And then let the machine learning layer actually figure out whether, what are the appropriate raw sensors that give you a good indication about those particular readings. And you can imagine the way you might do that might be different depending on which particular machine learning techniques you want to use. But this way, remember that the user or the programmer in this case is not writing code, right? They are giving examples of what they want the inferences to be, and then the machine learning layer should be able to address what, how to be able to provide those inferences at the right level. And you can't see at the bottom, but basically importantly in this case, the user is not even specifying which sensors are correlated with or would be useful for those inferences. You want the system to be able to figure out which of them are going to be important for this particular inference and which of them are redundant or noise, right? So you want to build a sparser model.
So is this the equivalent of essentially user specifying my user preferences for this case? I'm telling the machine, this is what I'm interested in.
Yes.
And then the ML layer on top learns that you like to open and close a door during this time of day.
Well, so that's one more level further.
Okay.
That's saying what my preferences are, what my policies are, what I want to actuate or not, right? So I think we'll talk about that.
First is more like you're getting these weak labels or sparse labels from your user population and using that to create a classifier without much data being required. The second is how can you, and we do support both, and I'll talk about that.
Okay, yeah. Cool. Yeah, so the idea is in the beginning, people don't even want to say, like, look, if Lux reading more than this, then the light is enough. Because I don't want to tell you, is it bright or not? And perhaps is it bright or not is dependent on different people's preferences, right? But I want to be able to learn those sensors without having to specify all of that itself, right? Not everybody wants to write classifiers. So on top of that, we have, yeah.
Can you give a non-trivial example of like these virtual sensors where you learn things from all the data?
So we have some simple examples right now, right? So meaning in terms of, are you asking if there's something very complicated?
Yeah, so door open. So I don't know, and this might be slightly sidetracked. I just wonder if you're trying to solve really harder a problem than you need to at that layer.
So whether we're using a much more sophisticated implementation to solve a trivial problem. Is that what you're asking?
Yeah.
I think The answer is yes for now, but we imagine that it's going to scale to much more challenging classification problems.
Okay.
Right? Because we want to know how many people are in a room, and we want the same technique to hold. We don't want to have to retrain users to think, oh, I have to think differently about how to answer this question, or how to get this question, how to create this classifier.
And I'll give an example. When we talk about the new sensing modality we're building, right, often there's like 50 different sensor streams that you don't even want to figure out which combinations of them are going to give you an accurate response of what you want to do, right? So the point is to take away all the manual training or things that you'd have to do to get a useful inference, right?
Sorry, one more question.
Yeah.
Does it mean that wearable devices can be used as well, like some kind of feedback loop between person's internal state and external environment? Let's say if my BPM is less than some specific values, then maybe I just lied a bit or something like that.
Yes. So you're talking about what actuation could happen,
Yes.
right? So a building depot, or sorry, our stack, the Giotto building depot stack supports both things, right? You have sensors and actuators. Now, this would be an example of an inference, which would be your physiological state,
Yes.
right? Am I feeling good, right?
Yes.
And is your feeling good could be composed as a virtual sensor that says, am I feeling good? Yes or no, right? And then you could say, the policy could be, if yes, then light up the Philips hue in green color versus light up as red, saying everybody knows, don't schedule a meeting with you right now, right? So that would be something that is supported with our stack. But the inference part is separate than what you do with that, because that's writing a policy. Right? And then we'll talk about that, saying that if you did that, which means that the point was every time the inference was that you weren't feeling good and you went and turned on something, then that could potentially be added as an automatic actuation saying like, look, based on what you've done in the past, I can learn what you actually want to do in the future.
Okay.
But I think you're covering that in the talk, right? Yeah.
Gotcha.
Does that answer the question?
Thank you.
Yeah. Okay. So this is what ties it together. So at the core of it, we have our middleware. Building Depot and Giotto are sort of used synonymously. So Building Depot is what we had started out with as a sort of building operating system, which we then expanded out to add all of these new capabilities that are there as part of Giotto. So if you hear both of them, think of them as part of the same core stack. In a building, you have lots and lots of sensors. You can't see them underneath, but you have lots and lots of sensor networks. And in the middle, we have this data management layer that provides data storage, contextual tagging, metadata, access control, everything that sort of allows you in a way to write applications on top. So I have a systems background. I always think of everything as sort of an operating system and like layering in terms of an operating system, saying these are the abstractions, these are the device drivers, these are the application APIs that people can actually write applications on top. And in the middle, you have this sort of scalable OS to be able to store, manage all of the data and resources that you have in this particular system, right? So you write applications that visualize, maintain, analyze, control, any sort of application that you want to write. So at its core, sort of our stack, this is what it looks like. So over the last year and a half, we've actually done a major update to our entire stack. So we are a Building Depot version 3 already. And the idea is that at the bottom, you have a myriad of different sensor networks. So think about sensor networks being your building management system. So BACnet, Modbus, everything that you sort of have, because a lot of the sensors and actuators are in real buildings that we already have. Then you have different devices such as BLE, ZigBee devices, various commercial off-the-shelf IoT sensors, Z-Wave sensors. So think about all of them, and then you have this abstraction of a data connector. Think of this as a device driver. That is either a protocol-specific device driver for all Z-Wave devices, or it's something specific to like this version of BACnet that Johnson Control runs on, right? So you have a data connector that enable all of these underlying heterogeneous sensors to be data to be collected and ingested. And then it's posted to a service called a data service. So think of the data service whose whole job is to store this time series data, primarily time series data. And we actually started out with various different databases. So we've actually tried out, starting off with even MySQL to Cassandra. And right now, our stack actually uses InfluxDB. As a function of that, we can actually, what we think, very easily switch this out into another time series database, and we're looking at Bigtable right now as potentially one of those examples where you could have one of these Google technologies and store that scalably. We also have things like caching so that persistent reads, etc., are speeded up. Now, all of these data services, think of these data services as this nice distributed system where you can instantiate as many data services as you want. You could have multiple data services for a particular building, or you could have the single data service represent multiple buildings. And then you have this notion of a central service. A central service takes care of all the metadata management, the permissions, the user groups, access control, etc. And it talks to your data service. Each data service also has a central service replica, again for high performance, so that you don't have to go to the main write-only replica of the central service. But standard distributed systems, we want to make sure that any updates are actually consistent across all of them, because we're storing metadata, access control, all of these things in these central services of who gets access to what. The central service is backed by a MongoDB store. And as I said, it's replicated. So each data service also has a copy of the central service replica.
You can finish that one.
Go ahead.
Well, so I was going to ask, where you see some, the basic question, of course, that Google thinks about all this is cloud versus on-prem for these, and where you see in this architecture that distinction might make a difference. Because some of the things you're talking about, replica, that as soon as you move to cloud, that's a given and obvious, right? Everything there is replicated and stored. It's like, that's what the cloud does. Whereas obviously when you get down to the sensors, that has to be local. And so functionally then, where does that distinction matter, in here?
So I think functionally, some of it is performance related. So remember, the moment you put things on-premises cloud versus off-premises cloud, think of this as an on-premises deployment of the depot, like our stack. You could imagine a hybrid architecture where you have all of your data ingest happening at a local installation, where some of the data actually, the long-term archival happens at Bigtable, or an installation in the cloud. Often what we found out is for many applications, you are actually doing inferences, you're doing actuation and control decisions where a 200 millisecond RTT to the cloud doesn't work, right? So often also what happens is that the data ingest may be so much that you don't, it's kind of immaterial, it's inefficient to siphon all the data to the cloud, do the inference that you want, and then, because the only thing you care about is the inference, right? It's much more efficient to sort of have a hybrid approach where you say, look, I'm going to do the inference locally, and then maybe my virtual sensor then gets pushed to the cloud, right?
You see that with these sensors, or is that?
No.
There's video, there's one thing, right? What is that?
No, but even these sensors, the problem is that we're just building a super sensor that has 314 sensor streams plus spectral features sending at 10 hertz or 100 hertz. No, that's that's a problem, right? Especially because the richer raw data you have, the better virtual sensors you can build. Do we really ship it to the cloud? Yes, you can, but at that point, that's not the right architecture to do it. Now, the biggest elephant in the room is that my campus will under no circumstance ship all their data to the cloud for even the campus backnet sensors, because there's privacy implications, there are other implications. So from a policy standpoint, even though it's not like the current building management systems are the most secure, they just have policy reasons for not shipping it out.
The problem is those are very fickle. Those can change both ways.
Yes.
Turn of the dime, right? So,
yes.
And that's why I'm trying to understand more of the technical, limitations
yes.
about the stuff. Policy, yes, I understand what those.
Yeah. No, I think it started out as that, right? Saying that no way is the data leaving, right? And we're like, okay, for many of these applications, because we need to do control decisions quickly, having to do them locally just makes much more sense, right? Often you want to do edge processing, so you don't even want to store the data inside your own premises, right? And then you have applications on top. Oh, this is a bit wrong. This is all HTTPS, if nobody noticed it, right? Yeah.
You would also imagine fault tolerance is a part of why you want to store data and have some applications running locally, right?
Yeah. Because if you so network partition, you don't want your building, just for your reference, right? There are some IoT systems like the Samsung Smart Things have found out that if you don't have internet connectivity, it just stops. You're like, okay, what, you're going to stop turning on my light now because you don't have good, and they sell that as a feature saying upcoming, it'll allow disconnected operation. It's like disaster, right? So I think for many things, you want the data to be local. So even if you become an island or a partition, you can actually continue to function. That's probably what you meant, right?
Yeah, right. And also you imagine that there will be lots of applications. really important applications controlling the entire, all these sensor networks.
Yes.
And exactly, it comes back to the point that you still want them to run and function in a proper way, even if it does not have access to.
Yeah, and a lot of the cloud level sort of replication and geographical diversity and stuff is useful for internet scale services. A lot of the applications here are useful for that particular installation or the particular campus, right? Having it replicated across multiple geographic regions does not make sense really for that particular application scenario, because it's not like the users are coming from all over the world, right? So I think some cloud solutions or some hybrid would be useful.
So what's the value proposition for your replication when you say the central server replica can be replicated?
So it's performance. So this one, the replication is for performance, and then fault tolerance so that you don't lose data.
Okay, but it means the performance the machine that it's running on aren't fast enough.
No, in this case, it's because you don't want all writes to go to your write-only replica, right?
Okay.
It's just standard distributed system, right? You don't want everything to be going to one write, so you don't want to have performance bottleneck there. So you cache everywhere else, writes go to one place, you don't have a consistency problem, right? Okay, cool. I'm going to continue. I'm going to summarize quickly what our stack features are, because I realize that we have till 10:15 for this particular talk. So apologies for this.
So much for your
there
time.
we go. So it's a completely distributed architecture. It is fault tolerant, as I mentioned. We're also doing load balancing because you can now have these distributed data services. You can start out with a data service for this room and then say, I'm going to go broad, which 1395 Charleston, or you can have a data service starting from Google. We also have an ability for you starting out with an installation and say, Google says, I am now going to install the Giotto stack. There's an ability to be able to sort of federate this at the level of like a higher enterprise and make sure you don't have to redo all that work again. That's something that we're still working on. There is a complete flexible representation of metadata and search. So everything is a key, sort of think of it as a key/value search. The interesting part is that what are the keys? We didn't pick winners in front of, like from the beginning, as in who would win out the schema ontology war, what sort of keys actually make sense. We have a templated schema so that you can import different schemas and ways to organize all your IoT sensor data. And in fact, very nice collaborative work. A number of us are presenting a paper at a conference called BuildSys, where we work together to come up with an ontology for smart buildings. We've also developed, this is all done as part of this project, so thank you for your support. Google is new developer APIs. And after testing all of the sensor inserts, we've had to add new APIs and additional documentation. We support both GET POST, so standard REST interfaces, as well as PubSub, because for many applications, publish subscribe is the right model of being able to do it rather than polling for data all the time. Somehow. Okay. This is a scalable tested implementation. So I realize that Google scale is not the same as academic scale. So I agree to that, but at least right now we've got multiple apps deployed. We have this working on 55 buildings at the very minimum, 200,000 sensors. And these are all sort of building management sensors. Many of these apps have been deployed for 3-4 years. Some of the newer ones since the starting of Giotto have been deployed for about 2 years. And these are running actual building applications that people use. We've also added a lot of management and integration aspects. I'm going to try to go through this fairly quickly now. The important part is we've also added a robust security and privacy layer. There'll be an entire talk about this, so I'm going to skip over this. Trust me on this, that when I said that we don't take security, privacy, and safety lightly. There'll be an entire talk about this. And we've also integrated a machine learning layer that Anand will talk about. Satya, who's not here today, their group has been working on this idea of how do you do distributed processing, saying how do you partition where the computation happens? Should it all happen at the local cloud? Should it happen at the data service level? Or should you push computation more towards the edges where the sensor data is actually being developed? So they've got this idea of a cloudlet or a mini cloud sitting much closer to the sensor. Think about your access point or even your on-hub router acting eventually as a little cloudlet that can do do some processing such that you can even enforce things like privacy policy saying, I can guarantee that the raw data never actually leaves even the first gateway. I'm only getting inferred sensors or sort of denatured sensors from that standpoint. They've specifically been looking at things that involve vision, which have a very clear privacy issue. And over the next, this year, our goal is to sort of formalize this architecture such that you should be able to move processing, at any part in this pipeline, whether it sort of follow almost like a stream processing type paradigm where you can move computation closer to the sensor or towards the actual data services, depending on what particular policies you want to implement. I'm not going to go over the security and privacy because, as I said, I have a whole talk on that. I apologize, this is really slow. So I'll talk about this in the next talk. We also have support for privacy. Again, I'm going to go over this in the next talk. I hope everybody's going to be here for that. But the basic idea for integrating privacy is that you make purposes of why your data is being accessed much, much more explicit. And we've got new programming abstractions that we've actually implemented that will make this easier. So unlike the sort of mobile world where we were all we had no control over what our apps are accessing at first, then we got much more control and it became like an information overload in terms of decisions people had to do. So we've actually learned from that. So Jason is another faculty member on this project. We've actually worked on mobile privacy for almost 4 or 5 years now. One of our apps has 250,000 users. So we've actually been learning from large-scale crowdsourcing of how people actually deal with privacy on mobile ecosystem, which is somewhat similar to what you have in IoT, a platform, apps, etc. And then we've also coming up with new ways to do privacy notifications that, again, I'll talk about. Now, an interesting part is the sensors and actuators. Our groups have a prior history in actually building our own sensor networks, doing all sorts of ZigBee sensors, etc. And including Anthony, who couldn't be here, has built a number of extremely cool systems for precise indoor location using ultra-wideband, VLC, ultrasonic, all of them to give you very, very precise indoor location, right? What we found out was that often we couldn't find this sort of one sensor that encompassed all. So most of the sensors were constrained by either low power RF, so it was like ZigBee or Z-Wave, which was bandwidth constrained, or they had to be low power by running on batteries, which essentially limited what they could do. Our hope was, if we took out those limitations, so we could have something that is wall-powered, Wi-Fi, no bandwidth limits, or at least what Wi-Fi gives you, what could we actually do, right, in terms of actual inferences and making useful applications that people would actually care about? So we built our own device called the supersensor. I can pass it around. This is the device that we build. The idea is you plug it into one of those little Apple adapters, and you have one of these sensors per room, and it has a myriad of sensors, 312 sensor streams, and a Cortex M3 underneath. And we're actually building an entire management infrastructure to be able to do over-the-air upgrades, getting all of this data, creating virtual sensors, push down all the way to these super sensors. And the idea is that you have many of these raw sensors, including time domain features or frequency domain features. So you have spectral features. You then pass them through a manual training and an auto learning layer so that you can learn events that the user actually cares about that can then be used by applications. This is the same pipeline for raw sensors all the way to feature extraction, to training, to finally sort of applications that can ingest those virtual sensors and synthetic sensors for doing something useful. So Anil will talk more about that.
What's the play? And maybe this is, I can ask this again.
Could you maybe say just very quickly your name and one sentence about where your question comes from, just because the conversation is much nicer if it's not that.
Oh, when we ask questions. Oh, I'm Trevor. I'm from Google. I work on the building operating system project. I'm just curious what the main motivation behind this is, just because a lot of people I know who are doing similar things are using Raspberry Pi, Tinkerforge things. You know, it seems like there's a huge number of things like this that are out there. So what are you really trying to push on with this particular
So this was the idea of developing the super sensor, was to develop one single device with the hope that it could provide complete coverage of everything that you might want in a room. right? Which means hope is that you have one device per room, maybe a few per large shared space, and it can sense everything that you might actually want to do in that. So put in all the sensors that people have proposed, except because they were, again, limitations on low power RF or power, like take all of those out and see if you can come up with one sensor that can do all of this. And enough computation that you can actually do synthetic sensors and these privacy layers all the way down to the sensors themselves. So we couldn't find anything. So you could buy 10 different devices and then sort of put them in a box and say, assume that this is all one box, but there was nothing as nicely integrated as well.
Well, I'll follow up on that later.
Yeah, so we didn't find any. If you find something that has all the sensors that we have, great. When we talk about the privacy layers, we're integrating things that notify people about what sort of like sensing is happening around them, and no current sensors actually do that, right? There is no notification about what sensing is happening in this particular room, for example. So it allowed us to a platform that we can augment and add to as we investigate.
Yeah, but you can do that. We'll follow up later.
I mean, you could put a Linux box and put everything on it, but that's not the point, right? Yeah, this is not a Linux box.
No,
yeah, sure. Okay, so example applications on top. This is what you might be wondering. So we have large-scale smart building applications. One of these applications that we just presented at Ubicom was on real-time feedback and estimation of heating, ventilation, and air conditioning, power management, as well as comfort for people. So everybody's familiar with that piece of technology that's at the back of you, right? It's a thermostat, where every room has it. People often hate it. At least on campuses, it seems like everybody hates it because it never seems to do the right thing. Our goal was, can we come up with a completely software augmented thermostat? Everybody's smartphone, everybody's computer, where you can actually not only figure out the temperature and control it beyond what the building manager might have decided, but also provide ways to give it feedback about how you're actually feeling physiologically. You can also figure out whether that particular zone is shared by other people. If you're in a shared space and two people want it really cold and the two people want it really hot, which is often referred to as temperature wars, try to figure out ways to deal with that. So Genie is a system that we came up with that is built on top of our stack, and 250 people actually now have been using it over about 2 years for controlling their indoor climate control for their personal spaces. And in terms of satisfaction, it went from 3 on 5 on a scale of 5 to almost 4.2 on a scale of 5 in terms of just people's comfort and happiness. And overall, it has led to the campus actually wanting to deploy this across all their buildings. It's a software application. We can actually do that, right? We can deploy it across multiple buildings. We've also come up with new way to visualize all of this data and make it easier for building managers. We've also come up with different algorithms for doing fault diagnosis. So look at all of this is time series data. So we've actually been able to sort of build machine learning algorithms that can look at all the time series data, build machine learning clustered models to be able to figure out how things should relate to each other, and then be able to figure out how many of them are actually real anomalies and what their energy impact might be. So this is actually being used by actual building managers to sort of like figure out faults. And interestingly, the campus paid, I think, $150,000 to a different company to commission and found faults. And we found ones that not only they had found, but we found even more ones, right, that they didn't even observe. So it's been so we had ground truth in terms of the faults that we were able to find using our framework. Again, all written on top of the same Giotto stack. We also have like mini applications. Sort of these are ones that use the underlying sensors that we installed. Anil will talk more about them. So example was, like find a quiet location with free seating. And this also gives you an example of where the raw sensors and the virtual sensors sort of come together. You could use audio sensors to figure out whether sort of a space is loud or not. You could have accelerometer on seats to sort of figure out if the seat is occupied or not. You could combine these virtual sensors to sort of make, when there are seats empty available in a space, can you notify me? That's what it allows you to sort of see how you can combine different virtual sensors to make even more powerful applications on top. And these are just examples of scenarios like people, places, and things. We're looking at, like now that we have our supersensor, we're looking at combining this into hackathons and even classes. So I'm teaching a new course on building IoT systems next semester, where we'll use these platforms to be able to sort of give people a much more hands-on experience with IoT.
Can you introduce yourself? Hi, my name is Pulkit.
Yeah.
I had a question about Genie, which you mentioned earlier.
Yes.
Where I really learned user preferences. I was just curious about how it matched to the user preferences, because it seems like you're listening to a lot of like sensor data.
Yes.
How we're learning usual preferences about what the temperature should be and how.
But they're using the user interface, right? They're using the Genie app to be able to figure out what they want to do. They're actually giving access to their Google Calendar or their calendar to figure out when they come in and when they leave, right? And then you can learn what their actually preferences. So this can be a reactive control, as in based on your calendar, based on your preferences, what should the temperature be?
So in the machine learning talk I'll give later on this morning, I'll talk about an inverse reinforcement learning technique we're using to do exactly that.
Cool to see. Okay, so are we done with the stack? No, many challenges remain. What I did tell you is that, look, we all know our buildings, our IoT sensors are going to be all over the place. They'll be very heterogeneous. How are you going to connect them into a common format where these portable applications can be written? Because Anand could call a bulb, I could call it a light emitting device. I could call it anything. How do we all agree on this common format? And how do you make sure that buildings and infrastructure that is 50, 100 years old, where people may have different views of how to represent things, are all going to come together? So we've been working on ways to sort of normalizing all of this metadata such that you can actually build these portable applications. As I said, we've also sort of figured out how existing schemas that are around, especially in the building space, are actually completely inadequate in terms of the coverage that they actually provide. So in fact, at the back of the room, we have Arka, who actually worked on this paper that showed that if you actually, depending on the number of buildings and the applications that people have written for smart buildings, if you look at some of these existing sort of schemas, you find out that they actually fall tremendously short in terms of sort of the coverage that they actually provide. And as a nice project, I think 16 authors or 16 or so of us worked together across 5 different institutions to come up with a way to sort of address this problem and develop a new system called BRIC, which is a new ontology for smart buildings. I'm not going to talk about it because I don't think we have time for that. I will leave these slides so everybody can see them. So basically, this sort of describes what design approach BRIC followed, and I want to mention that we've also been talking to several folk at Google. So this is an effort sort of that started out at Google called schema.org. So this was Guha, and we've been talking to a number of people there to sort of see how this new effort called IoT.schema.org could benefit from what we've been doing in the BRIC space. And the idea really is that sort of the way we could work with IoT.schema.org is that you could have all of these sort of layers that connect these individual systems such as Nest, SmartThings, Giotto, or any other building systems, and their schemas and write adapters that can actually then connect all of them to this underlying sort of IoT.schema.org vision, where you can then have sort of like IoT.schema.org could achieve what it did for schema.org in the web world, right? So that's what our goal is. And we've been integrating BRIC into our stack as well. And there are many other challenges that I haven't sort of addressed. So part of it is this sort of how do you handle this loosely connected sort of operation? As I said, many of these IoT devices are going to be connected through hubs, and the current models are all sort of broken in terms of disconnectivity and what happens when sort of you don't have network connectivity. And we need sort of architectural changes to be able to handle that, including where you do the processing. And even when you're disconnected, your sort of system continues to operate and then reconciles the state when the connection sort of resumes. And then also about how to sort of enhance the overall deployment use. As I said, we've got our stack sort of across 3 campuses, about 55, 60 buildings now. The idea is to actually even grow this out more and make it so easy that anybody, as I said, can sort of download and use it. And this is our goal to at least continue for this year, so that packaged version is available to everyone. It's been open source for a while, but the idea is to make it even more usable and easy to deploy and have some managed deployment. So if you don't want to have your own installation, at least you can sort of go to building, our IoTexpedition.org and then sort of start using it, even if you don't want to install your own, even to test it out. And many opportunities for collaboration. I apologize for running a bit over. So, but I can now take your questions. If you have any, thank you for asking questions in the middle, but if you have any more questions, I'm happy to answer them.